o'clock, so we are going to start right now. This meeting, just FYI, will be live streamed. You have two audiences, one that is in person, which you can see over here. Actually, I have three audiences. Two are the people who are currently at the Zoom meeting. And then the third audience is people who will watch it later on YouTube, because this is now going to be streamed onto YouTube. So I'd like to welcome our speaker for our Geography Colloquium today. His name is Dr. Vincent Lecours. He's an assistant professor of marine remote sensing and geospatial analysis at UF in the Geomatics department, but he is a geographer. He has a PhD in geography from Memorial University of Newfoundland. So he has a history in terms of working as a geospatial analyst, doing various things for the Quebec National Police, and working on deforestation in Peru, and doing land surveying in West Africa, and as a consultant for fisheries in Ocean Canada. So he does sound like he's got a lot of geography in his geographical background. And he's been showing up to the Florida Society of Geographers for the past few years. And so lucky for him and for us, he has agreed to be the vice president, which likely means he's got the presidency in his near future. So please welcome Vincent Lecours and Dr. Vincent Lecours, and take it away with your talk. Thank you.
Well, good afternoon, everyone. Thanks a lot for having me over. I've been at UF now for 5 years, and I've been following a little bit what's happening in the Department of Geography because of my background as a geographer. So I'm really pleased today to be able to share a little bit of what I've been doing at UF in the field and share that with you. So just to start, when people ask me to describe what I do, I say that I provide, or I try to provide, an interdisciplinary perspective on data collection and analysis for the study of the environment. So I was trained in geomatics, in applied geomatics in Canada, which the definition of geomatics is a little bit different in Canada than in US. Basically, I've been trained in remote sensing, GIS, cartography, and spatial analysis. And all of those backgrounds were always applied to the environment. For my grad studies, I started looking into the marine environments, because what I realized is that the marine environment really lagged behind in terms of the methods and technologies to efficiently study it, the knowledge of the environment itself, and the knowledge of ecological patterns and processes within the oceans. So at UF, I lead the Marine Geomatics Lab, and our motto is bridging ecological and spatial sciences. The main thing that we do is habitat mapping. And that term here, habitat mapping, really kind of describe well my affiliations at UF. So I'm affiliated with the Fisheries and Aquatic Sciences program and the Geomatics program. So my title today is Mapping the Marine World from Reef to Rift. And the reason why I picked that title is because I initially started my career looking at deep sea environment. So I did my grad studies in Newfoundland and Eastern Canada, studying things like underwater deep sea canyons, seamounts, and here that's the Flemish Gap. We used to map those environments and to study these environments, we use what we call a remotely operated vehicle. This particular remotely operated vehicle is as big as an SUV, so we need a crane to put it in. Yeah. What's that?
Are you wanting to share your screen?
Oh, I'm not sharing right now?
Right now.
Okay, let me try again. What about now?
Yeah, now you're there. Okay, thank you.
Okay, sounds okay. So yeah, I was describing this remotely operated vehicle, pretty big machine that is equipped with a lot of different instruments. The main one that I'm using for a lot of my research is a multi-beam echo sounder, which I'm going to describe in a minute. But it allowed us to explore these deep sea coral communities, which are pretty beautiful type of environments in the deep sea. But now that I am in Florida, there's not a lot of deep water around here. So I had to really go back in my background, look at what I used to do with drones and with land surveying, and adapt a little bit my approaches. So now that I'm in Florida, I do a lot of coastal mapping, looking at, for example, oyster reefs. We do drone surveys, fine scale 3D kind of complexity analyses of different types of ecosystems. So today I'm going to try to recover. I picked 3 case studies of things I've done in the past. 2 of them will be in the deep sea, and 1 of them is going to be in the coastal world. So the first thing I want to do is to define habitats, because I'm going to be talking about habitat mapping. Habitats are basically areas that are significantly different from their surroundings in terms of their physical characteristics, their biological characteristics, and their chemical characteristics. So habitat mapping, marine habitat mapping, is really an interdisciplinary undertaking. Most of the teams that I worked with are formed of acousticians and hydrographers, geomorphologists and geologists, biologists, ecologists, and oceanographers. And then in recent years, more and more, we're seeing spatial scientists and geographers getting into the mix. And this is really where I come in those groups. I'm helping my colleagues, ecologists and biologists and geomorphologists, try to collect the best possible data and information about the seafloor. So a typical habitat mapping workflow is quite simple. We go out, we collect a ton of data, then we process those data and integrate them into some type of habitat model. The habitat model can be many things. It can be, if we're taking more of a remote sensing approach, it can be a simple unsupervised or supervised classification. But we can also take a more ecological approach and do things like species distribution modeling. And that integration of data gives us habitat maps that we can then use for decision makings in contexts like conservation, management of resources, or restoration. So while I've been doing a little bit of data collection and looking at how we interpret and use maps in decision makings, the bulk of my work is methodological. So I look at data characteristics and how spatial data characteristics influence the habitat mapping workflow. So a few years ago, as a kind of new geographer into the field of marine habitat mapping, I did a literature review. I performed a literature review looking at how the geographic context of marine habitat mapping was considered. And my main finding was that there was a real lack of consideration of geographic concepts in habitat mapping practices. So despite being mapping, there was a lot of misuses of the different technologies and the different data sets that were used. So since then, the foundation of my research has really become about finding ways to better integrate or actually explicitly integrate geographic concepts into marine habitat mapping workflow. So some of the things I look into are spatial heterogeneity, spatial covariation, spatial data selection, spatial dependency or autocorrelation, spatial data quality, and spatial scale. So the different case studies that I picked for today's talk will actually only look at those 4 main geographic concepts. So we're going to talk about covariation, data selection, data quality, and spatial scale. So I'll dive right into it with my first case study that deals with spatial covariation and data selection. And I have to give you a little bit of background about how we proceed with mapping the deep ocean. When we try to map waters deeper than a few tens of meters, so beyond what optical remote sensing can help us gather about the marine environment, it becomes quite challenging to sample. So most habitat mapping efforts will rely on acoustic remote sensing tools. Like here, we have a multi-beam echo sounder. Basically, what the multi-beam echo sounder is, it's a sonar that produces sound at hundreds of little beams that are sent towards the seafloor at different angles. And then we get 2 main types of information from these kind of instruments. The first one is a little bit akin to LiDAR data, where we measure the time it takes for the sound to travel from the sensor to the seafloor and back to the sensor. And what we get is what we call bathymetry, or basically it's a 3D model of the seafloor, its depth values. But then, a little bit like radar data, we can also look at the backscatter, so the intensity of the returned sound. So if we have a hard substrate, for example, bedrock or boulders, the sound is going to be reflected strongly against these type of superficial geology, which means that we're going to have a strong return, a high backscatter. But if, on the other hand, we have a softer substrate like mud or sand, a lot of the sound is going to get absorbed by the seafloor, which means that the intensity of the sound returning to the sensor would be quite low. So we're going to have a low backscatter. So this information backscatter really allow us to look at the spatial distribution of the different types of sediments on the seafloor. So since multi-beam echo sounders are the best tool that we can use to collect information about the seafloor, it could mean that we have only two variables that we can relate to habitats. So we have bathymetry and backscatter. However, in the last 20 years, we found out that there's actually much more that we could get from that. We can use geomorphometry to give us more variables. So geomorphometry is the science that enables quantitative measurements of terrain morphology. It's basically terrain analysis. There are different types of geomorphometry, but the most commonly used in marine habitat mapping is the approach that uses a mathematical equation within a window of analysis, like here, that is then moved across the entire digital terrain model to generate values of terrain attributes or terrain characteristics of the entire study area. So by changing the mathematical equation that we can use within that window of analysis, we can derive things like slope, aspect, or the orientation of the slope, rugosity. And in fact, there are over 100 more algorithms of different terrain attributes that we can produce. The reason why these different terrain attributes have become important in marine habitat mapping is because we found that many of them are directly related to the presence or absence of different species. For example, if we take that species of deep sea corals on the right, we know that that species like terrain with a lot of topographic complexity. But other species like that sea pen here will prefer kind of a more flat, muddy substrate, and we'll use that strong muscular foot to actually settle on the seafloor, attached to the seafloor. So in summary, geomorphometry really allows us to move from having only two environmental variables, bathymetry and backscatter, to characterize deep sea habitats, to potentially having tens or hundreds of different variables. However, that can also be a problem in itself. We have to be able to make a choice of variable. So one of the problems is that there are so many options available out there in different GIS software that it becomes quite difficult to make choices about what to use in our habitat mapping workflow. So looking into the literature, what I found is that the choice of variables is often subjective or arbitrary, most often based on the availability of different GIS software and GIS tools. In most habitat mapping studies, before I performed that work, covariation and its impact on maps was often not assessed. So the main problem is that we have an increased availability of GIS tools that are user-friendly, that non-expert users can really use easily without necessarily having to understand the underpinnings of these different tools. A lot of those tools are black box tools, which means that there is no documentation that informs, for example, on which exact algorithm is used to produce different terrain attributes. What we know from experiments is that you can derive the same terrain attributes using different algorithms, different software, and they will give you different results that are actually not comparable. So when you have a non-expert user that doesn't have the appropriate guidance on how to use these different tools, it may lead the non-expert user to make a suboptimal or kind of a random subset of variables or terrain attributes to use. And these kind of random or arbitrary selection may lead to things like comparing elements that are not comparable. It can introduce covariation in analyses, and it may actually fail to capture the key properties of the terrain that are relevant to the studied habitats. So what I did to try to solve that issue, I was wondering which combination of terrain variables would avoid covariation and provide the most complete picture to describe the topographic environment. So what I've done here is generate different artificial digital surface model. So I produced 9 different surfaces, and I use fractal dimension to characterize their complexity. So for example, here in the top left, we have something that would look like a relatively simple valley, and it goes all the way to pretty complex types of environments. So when we're quantifying, for example, the complexity of coral reefs, we're actually in fractal dimensions between 2.5 and 2.7. So we really cover the whole range of what we could find in the environment. Then I used these 9 different surfaces and computed the different terrain attributes. So I used 11 different software that are widely available, which allowed me to find 200 different tools or algorithms of terrain attributes. So I computed those 230 terrain attributes for each of the 9 surfaces, and then use all of those surfaces into a suite of multivariate statistics. For example, I used principal component analyses, variable inflation factor, and mutual information matrices. But the main result that I got is something like that, where I got different components from my principal component analyses, and all my 230 terrain attributes would load on one of the different components. And the terrain attributes within the same component would be highly correlated, but terrain attributes from different components would be uncorrelated. And then each of these components would explain a certain percentage of the overall terrain variability. So if I wanted to find a good selection of variables to recommend using in marine habitat mapping, I simply had to find one variable from each of the uncorrelated component that explained the most variability on the seafloor. Actually, not the seafloor, on the artificial surfaces. And what was interesting here is that of the 9 different surfaces that showed different complexity, the order of the components would vary. So for example, for the most complex surfaces, the components describing terrain complexity would rank kind of higher, but the same 6 ones were always the top 6. So that allowed me to propose an optimal combination of 6 terrain attributes, which included a measure of relative position, so whether an area is more of a peak, a pit, or kind of a flat area, then a measure of rugosity or roughness, a topographic mean, then northernness and easternness, which are components of the orientation of the slope, and slope itself. And using these 6 different attributes basically reduces covariation and ambiguity in an analysis, maximizes the information extracted from the terrain, and increases generalizability. However, all of that analysis was kind of made in a more theoretical framework. So I was using artificial terrains, even if they mimic a little bit what we see in the real environments, it wasn't really kind of a real application. So I wondered if these different terrain attributes could form a standard protocol for using geomorphometry in different approaches to habitat mapping. So I had access to some data from offshore Nova Scotia in Canada. So you can see the Gulf of Maine here. And in this particular area, they collected multi-beam bathymetry data. So we see our digital terrain model here of the seafloor. From that bathymetry, I was able to derive 24 different terrain attributes, including the 6 ones that I recommended using. So for example, here we can see our rugosity. So we have areas of high rugosity, areas of low rugosity. And then we also had backscatter data from our multi-beam sonar. And finally, we had some ground truthing data. So a common thing to do in habitat mapping is not only to collect bathymetric data, multi-beam data, but it's to send, for example, here to drop a video camera on the seafloor and actually get confirmation of what we find there. So looking into these videos, we were able to classify different types of habitats on the seafloor, like reef, glacial till, rippled silt, rippled sand, and things like that. Here, these types of habitats are what we call abiotic habitats, because we characterize them using mostly the sediment categories. But we find that a lot of our deep sea species are actually strongly correlated with these abiotic habitats. But we also had some biotic data, so some sea scallop occurrences that were provided by fisheries monitoring data. So I use all of those data, so my bathymetry, my backscatter, different terrain attributes, and the ground truthing data into two main approaches to habitat mapping. The first approach, a top-down or unsupervised approach to habitat mapping, is quite similar to what we usually do in remote sensing. So we grab all our environmental data, put them into a habitat model, which is in this case, it's just a statistical classifier like k-means or maximum likelihood. And then we get a map showing discrete classes. And then we use those discrete classes and compare them with our ground truthing data to assign the statistical classes to a meaningful habitat on the seafloor. So the type of outcome that you get from applying that unsupervised approach is something like that. So we can see our different discrete classes on the seafloor representing the different types of abiotic habitats on the seafloor, and we can quantify some kind of accuracy of maps using our ground truthing data. Now, the second approach that we use comes more from the ecological literature. It's a bottom-up or supervised approach to habitat mapping. In this particular case, what we do is we use the sea scallops observation, combine them with the environmental data into a habitat model. In this case, we used maximum entropy from the species distribution modeling literature. What those models do is simply look at the environmental characteristics where sea scallops are found, and then try to predict the probability of finding scallops elsewhere. So what we get is a habitat map that is, in fact, a habitat suitability maps varying between 0 and 1. So we can get our areas of high suitability and our areas of low suitability. So what we did to try to confirm that those 6 terrain attributes were optimal to use in habitat mapping, we generated different combinations of terrain attributes and environmental variables. And we tested the appropriateness of the 6 terrain attributes that we recommended for habitat mapping. And also, as kind of a side project, we tried to describe the effects of subjectively selecting input variables for habitat mapping, which is what had been done prior to our work, which was, what was commonly done was subjectively selecting variables. So our main results, what we found was that the selection of proposed variables, the 6 terrain attributes I recommended, generally performed better than others. In the unsupervised approach, it discriminated individual habitat types better than any other combinations. And for the species distribution models, it had a higher predictive capacity and produced more robust and replicable model. But one of the side results of that work was really to see how variable different maps were. So for example, here, we use the same approach, the same algorithms, but we change only one of 8 variables. And we replaced it by another variable that was highly correlated with it. And what we found was that there was quite big differences in how our final maps looked. So here, what you see, those red pixels are those pixels that were classified differently in that map versus that map. And it might not look that important, but when you look at over the entire study area, you end up with differences, basically 566 square kilometers that are classified as a different habitat in different maps. And that matters when you bring those maps to decision makers. For example, if it's for the management of the sea scallop fisheries, it's important to know, for example, that gray habitat, is it covering as much area as this map, or as much as area as this map. So obviously that's kind of a best case scenario, changing only one of 8 variables, but we found that changing more than one variable or changing one for another one that is not correlated would produce much greater changes. And we measure changes varying from 10% to 58% across our different scenarios. And 58% of the area, that's 2,000 square kilometer. So once again, if, for example, if the green habitat class here is reef, and you know that reefs are ecologically important habitats, if you provide that map here to decision makers, they might just protect the shallow waters where the reefs are found or characterized by that map. But here, if you use that map here, you can see that there's a lot more reefs in the deeper water based on that particular map. So it's very important to understand and realize how much, how sensitive our entire habitat mapping workflow is to what we put into it. And we found the same type of differences in the more like ecological approach. So to conclude that case study, what we found was that spatial data selection is a very important step that can significantly impact the outcome of the mapping process. So what we did here was really highlight for the habitat mapping community the importance of actually thinking and justifying which variables go into our workflow. And then we also provided a selection of 6 terrain attributes that could form a standard protocol for using geomorphometry in habitat mapping. And since then, so that's been about 3 or 4 years since that work, these 6 terrain attributes have been adopted extensively by the community, and we see them being used quite a lot. So moving on to my second case study, dealing this time with data quality and spatial scale. One of the very common problems that we have in mapping the deep sea is that we have to rely on our bathymetric data as the main source of environmental information. However, bathymetric data often have visible and important artifacts in the data. So what you see here is a digital surface model of a little seamount in the deep ocean, and you can clearly see all those linear artifacts in the data. Unlike when we collect satellite imagery or aerial photographs or even drone data, our platform is not very stable when we collect deep sea data. Our platform and our vessels are impacted by the waves, by the wind, by a lot of the different environmental conditions, and a giant boat is not as easy to pilot than, for example, an autonomous drone. But all that motion that is introduced by the platform actually will impact how the sound is sent towards the seafloor and how it's received, which will then introduce those artifacts. So we got to be able to really account for that motion at a very fine resolution to be able to correct for those artifacts. So you can see 2 main types of artifacts here. We have those artifacts that kind of increase the complexity of the seafloor by kind of adding variability. And then we have some types of artifacts that are more of a spatial shift amongst different survey lines. So artifacts are quite common in bathymetric data, but rarely acknowledged because there's literally nothing we can do about it. Once you design your surveys and you've done everything to collect as good data as you can, they are just part of the data. In addition, those artifacts are usually within error specifications of the instruments, because the greater the distance between the sensor and the seafloor, usually the greater the errors will be on the seafloor, on the data. So we have an example here of something we would commonly see in the last 20 years in habitat mapping studies. So we have a pretty nice overall digital terrain model of the seafloor. We can see some pretty cool reefs and features on the seafloor. But what we can also see are, once again, those artifacts in the data. So all those lines that we see in the data, we even see some spurious soundings that should have been removed in post-processing. But the problem with using these data is that as soon as you do some type of classifications, like here for morphometric classes, these artifacts will show up in the data. So here, that entire area should be plains, but in fact, they are characterized as a kind of an alternate ridges and channels. And if you acknowledge the bias introduced in the analysis, that's okay. But in this case here, they actually quantified the relative coverage of the different morphometric classes, which obviously underestimated the amount of planes found and overestimated the ridges and channels. And then they carried that analysis further into actually assigning habitat classes. And once again, we can see all those little red artifacts in the deeper area, which were classified as deep rocky reefs, but should be classified as deep unconsolidated sediment. So this was quite common in the literature until the mid 2010s, because the impacts of data acquisition artifacts on the marine habitat mapping workflow were never quantified. We just we basically, most of us would just say, well, it's part of the data, it exists, and then we would ignore them. But then I was actually curious to see if we could quantify the error propagation of artifacts through the entire mapping workflow. So if we have artifacts in the bathymetric data, how does it impact our terrain attributes? And if those terrain attributes are then used to make habitat maps, how does that impact the habitat maps? So my main questions were, how sensitive are different terrain attributes to different types of data acquisition artifacts? And how sensitive are habitat maps to different types of data acquisition artifacts? And then I wanted to see if that sensitivity would vary with spatial scales, because sometimes what some users would do is, if there were a lot of artifacts in the data, they would just coarsen the spatial resolution of the data, trying to remove or to kind of average out the artifacts. So I wanted to see if the sensitivity, if that worked, basically. So I used the same data set, our bathymetry here, but computed the bathymetry at 5 different spatial resolutions that are commonly used in deep sea mapping, depending on the quality of the data we have. Then I artificially introduced 4 different types of artifacts. Artifacts caused by a roll of the platform, so when the platform is moved from left to right. An artifact introduced by the pitch of the platform, so when the platform is moved forward and backward. Artifacts introduced by heave of the platform, so when there's a vertical motion, for example, because of waves. And then another common one is a missynchronization between our navigation, motion, and multi-beam data. So by using my 5 different spatial resolution and introducing different levels of those 4 different artifacts, I ended up with 205 bathymetric surfaces of the same area, from which I derived the 6 terrain attributes that I recommended using, which gave me a total of over 1,200 terrain attribute surfaces. And then I went on to do quite deep analyses of the spatial and statistical distribution of these different bathymetric and terrain attribute surfaces. I looked at the surfaces that were assumed to be unimpacted by artifacts, those that were impacted by artifacts. I looked at the source data, which is the bathymetry, and the derived terrain attributes at different spatial scales, and basically modeled spatial and statistical distribution changes as a function of the level of artifacts that was introduced. So looking at the results for only the terrain attributes, what I found is that when there is pitch and roll in the bathymetric data, the spatial and statistical distribution of the terrain attributes were negatively impacted. But what I found is that for heave and time, only the spatial distribution was negatively affected. And that's because heave and time artifacts actually don't introduce variation in depth values. There's only a shift. Heave introduces a shift in vertical orientation and time in X and Y orientation. So the values remain the same. They are just shown at a different place. So that's why the statistical distribution was not changing, but the spatial distribution was. Then, as expected, we found out that the finer scale surfaces were much more impacted by artifacts than the coarser scale surfaces. So to some extent, it is a good approach when you have artifacts to coarsen your data resolution. And our main conclusion is that artifacts have a predictable and significant impact on the spatial and statistical distribution of bathymetry and terrain attributes. So no real surprises here. It's quite what we were expecting, but we were able to, for the first time, kind of demonstrate that and quantify it. But then we wanted to carry that further. So look not only at the terrain attributes, but how bad terrain attributes, bad bathymetry would influence our habitat maps. So I used those same 205 bathymetric surfaces with the 1200 terrain attribute surfaces. Use the two same approaches as I presented earlier, so our unsupervised approach and our supervised approach. And then I had different scenarios. So for example, making habitat maps using only terrain attributes, making habitat maps using terrain attributes and other environmental variables like backscatter to see if the addition of good quality data to bad quality data would increase the overall kind of quality of the maps. So in the end, I had 615 unsupervised habitat maps, so that top approach, and 615 species distribution models to compare. And what I was expecting is something exactly like that here, where at our reference surfaces, those that are assumed to be unimpacted by artifacts, we would get the most accurate maps at all spatial resolutions. And that as you introduce, for example, more roll on one side or the other, the overall quality of the map would decrease. However, we only observed that pattern for roll. For all other types of artifacts, it was almost completely random. In fact, we had about 50% of the maps that were affected by artifacts that performed better than our maps that were assumed to be unaffected by artifacts. And that's according to the typical metrics that we use to quantify accuracy of our maps. So things like the kappa coefficient and overall accuracies and all those other ones. So that was quite surprising. And what we found too is that those various metrics that we use commonly actually don't really represent well the proportion of change in introduced by the artifact. So for example, here we have a 0.2% difference in kappa between a map assumed to be unaffected by artifacts and one that is affected. But overall, 22% of the entire area was classified differently. So our main conclusion here is that the artifacts really had a non-predictable, but yet significant impact on the accuracy of habitat maps and the spatial distribution of habitats. So combining these two kind of little results, what we can say is that artifacts are important. They have an important influence. However, it's quite challenging to deal with them because the influence is predictable on the terrain attributes, but completely unpredictable when it comes to habitat maps. As I mentioned earlier, we're currently limited by technologies, so we often cannot correct for the artifacts. We do the best we can to reduce them when we collect data. We do the best to account for them when we post-process the data, but ultimately, if there are artifacts in our bathymetry, there's not much we can do. So a lot of my work following these two studies was to start identifying sources of artifacts and how we can better account for them or prevent them at the very beginning of the workflow. And that's something I won't dive too much into today, but that was really kind of the foundation that drove me to work towards improving data quality in habitat mapping. So moving on, we're actually coming back to coastal habitats in Florida. So that's going to describe a little bit more of the work that I've been doing recently. I haven't abandoned the deep sea. I still have a lot of collaborations dealing with deep sea habitats, but studying coastal habitats in Florida has been quite stimulating and interesting because the tool sets, the different tools that we use to map these habitats is quite different. So to give you a little bit of context, coastal habitats in Florida are quite important. They provide a wide range of critical ecosystem services. For example, they protect us from erosion. When I say us, I mean the coastline. They protect the coastline from erosion and storms. They provide good opportunities for tourism and outdoor activities. They provide habitats for other species. They enhance the fisheries. However, many of these habitats and the services they provide are also facing extreme pressure, whether we're talking about unsustainable tourism, inadequate protection and management, climate change, pollution. And the state is working really hard through the Florida Fish and Wildlife Conservation Commission to restore and start monitoring program for these different coastal habitats. One of the problems currently is that ongoing restoration and monitoring efforts don't have baseline data against which to quantify success. So for example, the main oyster spatial data set of the state of Florida is more of a historical footprint. So when you look at the attributes of each oyster reef in that data set, you can see that the last time they were surveyed sometimes is 50 years ago. Sometimes it's 2011, sometimes it's 2017, but it's so variable that we don't have currently a good understanding of the health of the oyster resources in the state. So the need that I'm trying to address with all that work is the need for frequent, effective, and comprehensive mapping and monitoring methods for different types of coastal habitats. So my lab has been trying to implement a multi-scale framework for coastal habitat mapping and monitoring using remote sensing. So we have some projects looking at the entire state, trying to find the areas where a lot of critical ecosystems are found. So there's a lot of effort and monitoring efforts and understanding of the Florida Keys because it's such an emblematic ecosystem, but there's also a lot of very important ecosystems, for example, in the Big Bend of Florida. Then we take an approach where we look more at the ecosystem level of individual estuaries or a network of estuaries. And we also do some very fine scale work trying to understand fine scale topographic complexity and how it relates to different health metrics used by ecologists and people involved with studying oyster reefs in this particular case. But what I'll be focusing on today is really the estuary level. And what we've learned pretty quickly is that even if you're interested in oyster reefs, you really have to take to an ecosystemic perspective. Because, for example, here, we have some oysters, and when if the oysters are not doing well and they start failing and getting carried by the water, that entire area is going to turn into a mudflat. But that mudflat will quickly be occupied by a infringing salt marsh. So there's a strong dynamic relationship amongst different types of coastal habitats that really has to be considered when you're studying any of these different types of habitats. So when we started getting involved with that kind of work, we went with a pretty basic approach at first, where we collected drone data above some estuaries. Like here, we have the Little Trout Creek, which is an area between Cedar Key and Suwannee on the Gulf Coast of Florida. And in this orthomosaic, you can see, for example, some mudflats, some salt marshes, and some oyster reefs. And then we use these orthomosaics into an object-based image analysis workflow. So for those who are not familiar, instead of grouping individual pixels into classes or assigning pixels into classes, we first group we first group similar pixels together into objects, which segments the imagery like here. And then it's the objects that we classify instead of the individual pixels. And the kind of classifications we would obtain is something like that, where we get the relative coverage of the different habitat types in our orthomosaic. And those early classifications gave us an accuracy of about 80%. And we weren't very pleased with 80%, so we started looking into the causes of that accuracy. And one of the challenges that the water and the tides movement really caused some spectral changes and artifacts once again in our mosaic. Obviously, a wet oyster is going to look differently spectrally than a dry oyster, and same thing with mud. But also, when we collect these data, we're always fighting with the tide. So we're going at low tides, but the tide often comes in. So you can see that those kind of lines in the data, that is caused by the water being slightly higher at every pass of the drone. And what we found too is that our spectral response of each habitat type was quite similar. So, for some purposes, an accuracy of around 80% could be good enough, but for accurate temporal monitoring, we thought that we needed to do better. So the first thought we had was to use structure from motion photogrammetry to produce a digital surface model of our different habitats, and then use geomorphometry like I've been doing in the deep sea. But that hasn't really improved our classifications. And the reason was because those different terrain variables were produced using a default 3x3 window of analysis, so looking at a very fine scale. But what we know from the literature is that different habitats are usually characterized by different patterns that will relate to different ecological processes at different spatial scales. So in ecology and in geography, it's well known that single scale studies may actually fail to capture the relevant patterns and processes. So the solution we've been trying to implement is to use multiscale analyses, which can be implemented using different approaches. One of them is simply through coarse graining. So resampling or averaging our observation data, or the spatial resolution of our data. And what we've found so far is that statistically speaking, the performance of the classification doesn't vary significantly with spatial resolution. And that has strong implications for when we plan our surveys, because if we don't need a 1 centimeter resolution, that means we can fly our drone higher and get more coverage on the same battery charge. And it also improves processing time. But then we started looking at the individual habitats instead of the entire ecosystem. And we found out that the classifications provide the best results at different observation scales for each habitat type, which really confirms that a single observation scale isn't optimal for all habitat types. So right now we're trying to look if we can integrate data, different spatial resolution, if we can improve our overall classification accuracy. Another way to implement multiscale approaches is to keep the resolution of the data constant, but this time change the window of analysis. So instead of using a 3x3 window to compute, for example, a slope, we can actually use a 5x5, 7x7, 9x9 window, which will cover a greater area every time. And this is an approach that we've been using here. That's just that's an example of deep sea mapping that we did in the Arctic. But the idea here is that we had 14 different terrain attributes that we computed using 8 different windows of analyses, and it gave us a lot of variables. So the problem with these kind of approaches is that it quickly becomes cumbersome. There's a risk to introduce covariation in the analysis. It's computationally intensive. It's quite challenging. So we wondered whether we could integrate these multiple scales into one single dataset. And one of my colleagues in Canada actually did just that. He provided a tool in his open source white box tools GS software called Multiscale roughness. And what that tool does is basically compute roughness using a range of windows of analysis, and then extracts the maximum roughness that was measured and outputs that maximum value of roughness, but also the scale at which it was calculated. His approach has been tested, and before we started playing with it, it was only used at the landscape level for geomorphological studies. So we wondered if we could apply it at very fine scale in an ecological context. So we used the tool on our digital surface model, and that's the output that we got. So you can see, for example, here areas of high roughness, areas of very low roughness at various that were measures at various spatial scales. Comparing that with our classifications, we're able to kind of characterize the topographic complexity of each habitat types. So for example, what we found is that our marshes had the highest level of roughness And that roughness was measured at the finest spatial scale of all habitat types, which makes sense because we have a digital surface model that captured the top of the vegetation, which is highly kind of produces a lot of rugosity. Then, as expected, our mud flats at the lowest values of roughness, and the maximum values of roughness for mud were found at the broadest spatial scales. And then our oysters were kind of in the middle, but closer to our marshes. And what's interesting is that here we could find the median scale of roughness for each habitat types and multiply it by the spatial resolution of our data, which was 6 millimeters, to get an actual ecological scale that is optimal to characterize the patterns within each of these habitat types. So we were able, for example, to identify 1.5 meters as an optimal scale to study salt marshes, 13 meters for mudflats, and 5 meters for oysters. So in conclusion, that work is currently showing that we can actually differentiate coastal habitats using their multi-scale topographic characteristics, which means that we could potentially develop topographic signatures to complement spectral signatures that we commonly use in these type of classifications. So just a quick few examples here. We have a salt marsh patch surrounded by oysters, and we can clearly see the pattern in our multi-scale roughness really captured that salt marsh habitat patch. Here, what's interesting is that mudflat is actually covered with individual oysters that we cannot see using only spectral information. But these individual oysters were really well captured in the multi-scale roughness tool. So that can potentially contribute to better abundance estimates for oyster resources in some estuaries. And then the last example here, we have our oyster reef with some propeller scars, and we can see that density of oysters varies on the surroundings of the oyster reef, and that is well captured once again in our multi-scale roughness. So to conclude this final case study, developing topographic signatures for different coastal habitats is promising to address some important surveying and sampling challenges associated with these type of environments. So here we're not dealing with any of the spectral artifacts that we had that was caused by the water. So multi-scale approaches are quite promising to improve our coastal habitat classification workflow, but there's still quite a lot of work to be done to fully understand the complexity involved in combining different observation and analytical scales and the role that they play in coastal habitat classification and monitoring. So this is something that I've been working on with a lot of different collaborators, trying to understand the suitability of different multi-scale terrain attribute approaches for habitat classifications. So our next step that I'm currently working on is to extend the analysis to other multi-scale variables like multi-scale topographic position here. This past summer, we collected LiDAR data, and we want to compare a digital surface model with a digital terrain model computed from both structure from motion photogrammetry and LiDAR. And the assumption here is that once we remove the vegetation layer of salt marshes in the digital terrain model, there's going to be a huge difference, but the oysters is likely going to remain the same. So anyway, we're exploring that. Then we want to integrate these different multi-scale variables into our workflow to see if we can improve the accuracy. And this past month, we've been collecting acoustic data in that same area for subtidal oysters, so the oysters that are always underwater. And we want to compare their topographic signatures with those intertidal oysters. And we're also experimenting with underwater photogrammetry to get 3D models of subtidal reefs. And the last thing is we actually got a new drone in the lab, a vertical takeoff fixed wing drone equipped with 2 multispectral camera that collects 10 different spatial bands. And we want to see if adding 7 bands to our workflow will actually improve it or not. I mean, it's really cool to use these technologies, but I kind of hope it won't improve the workflow because we're trying to provide tools for the state agencies to better monitor. And the state agencies don't necessarily have the funds to acquire super fancy cameras. So hopefully we would be able to find a workflow that works with a cheap drone that they can buy and actually collect their own data. So we're really balancing here the coolness of research versus how actually useful it is for the stakeholders. So in conclusion to my seminar, those were just 3 case studies of things I've done in the past or I'm currently working on, but there's a lot more work being done in our lab by students. One is currently assessing the ecological impacts on coral reefs and mangroves of an oil spill in the country of Mauritius in the Indian Ocean, using remote sensing. I have another student doing automated detection of marine mammals in drones and satellite imagery, including of manatees in Florida, to try to improve counts in rivers. I'm also currently doing some modeling of cold water coral species distribution in the Gulf. And I'm collaborating with the Department of Anthropology to collect seafloor data for underwater archaeology. And I have some other projects in the deep sea in Brazil, Norway, and Canada. The main thing that links all those projects is what I mentioned at the beginning. We're really trying to introduce, or in some case, reintroduce spatial context into the habitat mapping workflow. We want our maps to be as good as possible. We want our colleagues that are specialized in ecology and biology, in deep sea geology, to be able to make the best use of their spatial data and workflow. So our goal is to help practitioners and users and decision makers make better use of their spatial data, which would eventually result in better maps and models that we can trust more and hopefully more informed decisions. So last slide, basically, marine environments are quite multidimensional. They are quite complex. We're trying to connect chemical data with biological data and physical data that are collected at different spatial scales, at different temporal scales. It is quite challenging to do, but mapping marine environments really requires an interdisciplinary approach that is grounded in geography, grounded in the tools that geography has provided and continues to provide, but also in the foundational geographic concepts that supports geography. So that was quite a lot of content. I thank you for your attention, and I'm available to answer any questions.
Okay, thank you very much, Vincent. Very interesting talk. Questions from either the Zoom audience or from the live audience here?
Hi, I have a question.
Sure.
So thank you for your presentation today. I really enjoyed. I'm an oceanographer and I felt like back home during my undergrad program. So you talked a lot about spatial scale today, and I was wondering what are the main challenges associated with habitat mapping in terms of temporal scale and temporal variability, since data is more limited, not so frequent. Is there any interest or effort towards that?
Yes, definitely. Unfortunately, there's actually not that much effort because mapping deep sea habitats, for example, is so expensive that we rarely have the means to go back and sample a second time. So most of the data we collect is really a snapshot in time, and it's really difficult to integrate the temporal component into that. It's much more considered in coastal habitats because, for example, in Florida, we have a lot of temporal variability in our seasons. So, for example, the different estuaries that I'm looking at right now on the Gulf Coast are really close to the Suwannee River, which feeds a lot of sediment into the water throughout the summer, but in the winter will come down, and then we're going to have more clarity in the water. So long story short, in the deep ocean, the temporal component is not very well considered just because we can rarely repeat our observations. But in coastal environment, a little bit more, but still not, there's not a lot of work done on it.
Thank you. Anyone else? I'll ask one question. How do you assess heave roll pitch on a moving boat?
So you need one of two instruments, either an inertial motion unit or inertial navigation system, or just a regular motion unit. But usually what will happen is that because we want to correct or to account, to really capture that fine scale motion, we're going to use Kalman filtering. So we're going to have multiple instruments that tries to capture that motion different ways, and then use a Kalman filter to improve our solution. And then all that motion gets applied to the acoustic data. So for example, if there's a roll and the sonar send the sound a little bit sideways, if we quantify that roll, we're going to be able to kind of position it properly on the seafloor. So when you look at acoustic data, actually, usually we have overlap between our adjacent lines to make sure we don't have gaps. But on the surroundings, or if you're just running transects, you're going to see the data is going to be a bit jagged. And usually it's jagged just because we're correcting for that roll data.
Okay, thank you for that answer. Anyone else? Okay, well, we really appreciate your time and talking to the department, and hopefully people who have common interests will connect with you, and we look forward to connecting with you in, I guess, is February at the FSG.
Yes, thank you very much.
Okay, see you there. Thank you for coming.